So and these are the basic definitions that we have discussed in the last class. So a random process is the basically the set of all the possible outcomes of a certain, random experiment. So if we take an example, we can take uh, the situation where we are receiving different calls uh, from a certain transmitter at different time instances, right? So we can consider those different calls as outcomes of a random process. So if we take call 1, we can observe its signal power against the time, and we can plot the amplitude variation. So similarly for call number 2, we can do the same thing. So likewise, we can do we can have the signal against time plots for all the different calls. So the different calls in here represent the realization of the random process, which means that realization is one individual sequence that can be an outcome of the random experiment. Okay, so one outcome is known as the realization, and in this case, the outcome is not just one number; it is a sequence of numbers. It is a sequence of outputs. So basically, realization looks like this, where we consider a realization as one outcome of the random experiment. When we take all the realizations that are possible, we call that the ensemble of the random process. So the ensemble we normally uh, uh, study using time instances. So we can define the characteristics of all the realizations uh, by considering one time instance at a certain time. So if we want, we can consider t equals 1 second, and then we can plot the amplitudes that we can obtain uh, for a time instance of 1 second of all these realizations. And using the probability theories, we can plot the probability density function. So for a normal call that is received, the probability density function will be a Rayleigh function by theory. So likewise, we can do the probability density function analysis for each time instance of the realizations or of the ensemble, right? So for t equals 5 seconds, we can take the amplitude of all the different realizations, and we can plot the probability density function related to the amplitudes that we observe at that time instance. So uh, the 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 time instances are basically the random variables in these random processes, right? So random variable is basically actually the time instance, right? So we actually consider one time instance, and we plot the amplitudes in that specific time instance and observe its characteristics and its other its characteristics. Basically, it's a probability density function, its average or the mean value, then its variance value, right? And all the statistics that we can mathematically model, we will use to understand the amplitudes of the signal at time equals 1 second. So at time equals 1 second, we have certain amplitudes that we get for all the realizations. We are going to analyze them using the statistics such as mean, variance. Then we also discussed about autocorrelation on autocovariance. Those statistics will be used to study these amplitudes of this signal at a certain specific time instance, right? So for a specific time instance, we consider that specific time instance as the random as uh, one random variable of this random process, right? For each time instance, we can consider that that time instance is a random variable. What I mean is that if you consider another time instance, let's say t equals 5 seconds, that time instance is another random variable of this random process. So this random process is defined by the random variables, which are again specified by the time instance, basically, right? So that is the basic idea that I want to discuss with you regarding the random processes and the random variables in that random process, right? So if you have any questions, you can ask. And I believe that if you did not have time to write the note, I believe that you possibly you could have, written the note using this note that I shared with you. Apart from that, like today, if you feel that you cannot catch up with the lecture, then then if my speed is high for you to catch up, then you can maybe put a message in the chat for me to maybe delay a little bit so that you can note down the most important things. However, I think you can write the note after the class, because I think that this time of 3 hours might not be sufficient to cover all the content that we have we have as to be, we have to cover. So so sometimes you might not have the time to write every single point, but in that case, that you can maybe write it later. So we discussed about these random variables in the random process. So basically, random variable in a certain random process are actually the time instances at which we are observing the observing the realizations. The definitions of these realizations, ensemble, those things we discussed. And basically you can actually remember these definitions to to get a clear understanding about the random process, and also quickly understand when a certain statistic is defined based on these definitions. So we discussed about the ensemble average also. So ensemble average means that the average that we can obtain for the certain random variable xt, which is defined by the time t at a certain time value. And this average ensemble average we can obtain by considering the probability density function of the xt random variable. And if right, so xt random variable we can obtain, and we can obtain its probability density function, and then we can use that probability density function and the random variable to find its average value. The average value we can compute using this integration, right? So we can take the product between the random variable and its own probability density function. Once you have computed this, ensemble average, you can find the mean value of the random variable xt, or in here it's x1. So x1 correspond to the variable at time equals 1 second. So the variable mean we can find using ex1. So mean means like the middle point where the distribution is centered around, right? So the ensemble average will give the mean value of the random variable x1 around which the distribution is centered around. So it gives us the place in the distribution where the peak of the probability density function is found, basically. The peak, or the place where the probability density function is maximum, right? Or we using that value, we can find the most most common most common random variable which has the highest probability of occurring. So in that definition about the ensemble average, we also discussed about another thing, another point, and uh, which is actually that the ensemble average is constant. If at a certain if in a certain random process, if we observe that the ensemble average is constant at each point in the time, we call such process stationary random processes, right? So ensemble average, or this EX1, is equal at each time instance. That means that in here we have considered EX1. 1 means 1 second. So similarly, if we compute for 5 seconds, let's say EX5, and if we see that EX1 and EX5 are equal, and also if we see that for all time instances, it is equal, right? Then we can say that the random process is a stationary random process, right? We can say that it is stationary random process if the if the value of the ensemble average is constant at each point in the time. So another thing we noticed was that uh, another process called ergodic process. And in the ergodic process, the ensemble average will be equal to the time average of any single realization. So in that case, the average that we observe as the ensemble average will be equal to the time average that we can calculate per each or per any realization where we consider the average over the time. So that means we are considering the average in this axis over the time domain. So the average we can find using this integration, right? And the time average we have taken using this limit capital T goes to infinity and 1 over t integration minus t up to t, then xt dt. Right? So what does this function do? Right? So what does this function do? So this function basically finds the average of the amplitude, right? Find the average of the signal amplitudes, or by taking into consideration all the signal amplitudes over the time. And then since it is not a periodic signal, the average is found by sending the time period up to infinity. The time period is given by the capital T here, and the capital T should be sent to infinity because this signal, which is not a periodic signal, will be periodic when the period is actually reaching infinity. So what we mean is that a signal which is not periodic, which is not showing any pattern, periodical pattern, then it is having its period, or its repetition will occur at a infinite time of period, which means that it's never going to happen, right? It's never going to be period. It's never going to be periodic. And then to show that, we are sending that capital T period to infinity to show that this signal is not a periodic signal. However, we are using the conventional integration even inside this circle to find the average of the time signal using the integration for finding the average in a periodic signal. So anyway, after finding the time average, if we observe that the time average value is equal to the ensemble average value, right? Ensemble average value we can obtain by taking the average over all the amplitudes we can observe in a certain time instance. And then time average we can find by taking the average of all the amplitudes that we see over all the time instances. And if we see that those amplitudes that we find as the average are equal, then the process is known as a ergodic random process. So the importance of this ergodic random process is that we can analyze a certain random process just by looking at the time realization only, right? Just by looking at this time realization, we can predict the behavior of the total ensemble of all the realizations of the process, right? So by only, trying to, study one realization, we can predict the behavior of the total realizations in the random process, which is an advantage for us where if we have like thousands of realizations in the random process. So in that case, the computation is simplified if the process is a ergodic random process. So by looking at one time realization, that we can, we can predict the behavior for all the other realizations. So do you have any questions? We also discussed about other parameters related to the ensemble and in the last class, and we defined the mean of the ensemble, its mathematical definition, and also we defined the variance and how to find the variance of an ensemble. Right, so remember, ensemble is the random variable that we define for a certain specific time instance, and we can find the ensemble statistics by considering the values of the realization at a specific time instance. So if we take time equals 1 second, that is the time instance where we will be observing the entire realizations and observing the characteristics of the amplitudes of the signal at that time. So we can define the variance and mean for such kind of such a time instance in the random process. So the mean and the variance we can define as ensemble mean and ensemble variance. Apart from those definitions, we discussed about something called autocorrelation. So autocorrelation is the process of finding similarity between uh, two time instances uh, of the same uh, signal, right? So, for example, like if there's a certain realization, if there's a certain random process, right? If there's a certain random process, we can consider the similarity between two random variables, xt1 and xt2, right? So the similarity that we can see between this xt1 and xt2 is what we call as autocorrelation, right? So in the same random process, we have two time instances where we call uh, T1 and T2. And those time instances and xt. So I think I got a call and this got disturbed. So I will explain using this diagram. When we have this random process, right? So this entire figure with all these realizations is the random process. And if we want to find the autocorrelation, we have to consider two random variables in this random process. So the random variables means basically the the variable that is formed when we consider one time instance, right? So if we consider one time instance, let's say t equals 1 second, then we can consider that the the distribution and other statistics of the amplitudes for that specific time instance, 1 second. And then for timing instance 5 second, we also can consider another random variable. And then if we want to find whether there's some similarity between this time instance 1, time instance 5 seconds, then we will use the autocorrelation function to find the similarity between these two functions. Sorry, these two random variables, right? So to find the similarity between these two random variables, we use the autocorrelation function, right? So basically what we are doing is we are trying to find the similarity between one time instance and a lagged version of the signal which is occurring at t equals 5 seconds, right? So uh, t equals 5 seconds is a lag or time I mean an instance that occurs after a certain time delay with respect to the first time instance that we are considering. So anyway, we will use autocorrelation to find the random variables, similarity between the random variables that occur at t equals 1 second and t equals 5 seconds. So autocorrelation function is very important function, mainly because in order for us to, for example, in signal processing, if we want to find out the position where two signals are very similar, and then if we want to align the signals such that the combined signal of those two signals has the most power, uh, and also make sure that there are no cancellation between the two signals when they're combined, we can find this, we can use this autocorrelation function to find out the lag between such kind of, between the, signals, and we can find out at which point the signals are very similar. So correlation means basically finding out the similarity between 2 points in the same random process, right? So autocorrelation means the function that finds the similarity between two time instances of a certain random process. So that we can find using this, like integration, where we take the expectation of the random variables product between xt1 and xt2. And if we take the product, then we have to take the integration like this. So the product of the two random variables xt1 and xt2 will be multiplied by fx1 and x1 and x2. So this fx1 comma x2 correspond to the joint PDF. And then that will result in the autocorrelation between these two random variables, and we can find the value. For a discrete random process, you will need to use the summation instead of the integration to find the value of the autocorrelation. So the function that is performed is almost the same. Only difference will be using the summation function instead of the integration. So autocovariance is another parameter that we take into consideration when we are analyzing random processes and the random variables in the random process. So if there are two random variables at T1, between those two random variables are defined as given in this equation, where the covariance or autocovariance, right, is equal to the autocorrelation between those T1, T2 time instances minus the product between the mean value of T1 time instance and the T2 time instance. So autocovariance is also some important function that we need to use to find the behavior of a random process. So we learned about these statistics in the last class. So those statistics are very important for our class today to identify the different properties and features of random processes. So we discussed about different types of random processes in the last half of the last class. And we discussed about different types of random processes. So there are random processes which are independent random processes. And these independent random processes are processes where we can say that the random variables in the random process are independent to each other, which means that there's a random process which has variables xt1 and xt2, right? So the variables are defined at t1 and t2 time instances, and those random variables are defined using xt1, then xt2 likewise. So these two random variables, if they are found to be independent, which means that if one is varying, the other does not get impacted by it. Similarly, if x2, xt2 is varying, the xt1 is not getting impacted by it. That is the case, then we can consider that the probability distribution function of such kind of an independent random process can be mathematically defined as each individual PDF of the random variables multiplied together uh, as, can together represents the joint PDF function of the uh, of all the random variables in the random process, right? So the joint PDF function of all the random variables of the random process can be equal to the product of individual uh, each individual uh, probability density function. Then we discuss secondly about the independent and identically distributed random processes, which are known as IID. So IID random processes are frequently used in random uh, random processes and in random signal processes. We so the main feature of the IID process is that all the random variables of the random process will be having the same PDF function, right? So in here, the apart from being independent, the additional thing is that it is having the same PDF function at each time instance, which means that the PDF function at xt1 and xt2 are equal, which means that if we consider the expectation operation of the random variable xt1, it is equal to the expectation of the random variable xt2. And that will be a constant value. I mean, it would be a fixed value. So if we want to find out the autocorrelation of the random process, which is IID, then we can see that since it is independent, we can write the autocorrelation as equal to ext1 into xt2, which can be expanded further as the product between ext1 into ext2, right? So the second line came because of the independence between the xt1 and xt2 variables. Thirdly, since the process is identically distributed, we can say that this mu value of each time instance is equal. So which means that the autocorrelation function will be equal to mu into mu, right? Because xt1's expectation value is mu, xt2's expectation value is mu. So if we consider that case, then the mu into mu will equal mu squared, which means that autocorrelation function will be mu squared. And then we discussed about uncorrelated random processes. So thirdly, we discussed about the uncorrelated random processes, and uncorrelated random processes are also similar to independent random processes in some way, however, not completely equal to independent random processes. So what I mean is that if there's a random process which is independent, it will always be uncorrelated random process. And however, if there's a random process which is uncorrelated, we cannot ensure that it is going to be independent random process. The reason being uncorrelatedness is measuring only the linear relationship between the random variables, right? There could be a nonlinear relationship between the random variables, right? That are defined at each time instance. There's some kind of a nonlinear relationship, then that means there's no independence between those random variables, right? However, in independence, it means that all the linear, nonlinear relationships are not there, which means that uncorrelatedness does not ensure that it is an independent random process. So uncorrelated uh, can also have some other dependencies between the random variables. So I think uncorrelated random processes we discussed about, and then we wrote the definition related to the uncorrelated random process. Uncorrelated random process is also showing the behavior of this expression similar to the independent random processes, where we take the expectation operation of the product of xt1 and xt2, and then we so there should be a bracket coming here at the end, right? A bracket is missing. So xt1, xt2 product and its expectation value will be equal to the expectation value of xt1 into expectation of xt2. So this expression is valid for uncorrelated random processes. I think we stopped at that point. Then today we will discuss from that point and onwards we will discuss. So if you have any questions, please let me know. So in today's class, I'm hoping to give you a quiz, and I will give that at a point that I feel like giving it. I don't know at what time I will give it. So like I will give a quiz related to what we have done. So right. So if you have any questions, you can let me know. So I think we have discussed what we covered so far in our class, and today we will do like a bit extension to that part, starting with multiple random processes um, and the characteristics of multiple random processes, which can be defined using the parameters known as cross correlation and cross covariance. So multiple random variables. Sorry, multiple random processes. Right, multiple random processes. So if we have, for example, two random processes, right? Two random processes that are different, right? We call those random processes multiple random processes, or uh, I mean, studying such kind of random processes which are different, we call as the study of the multiple random processes, right? So the multiple means like we are going to consider different uh, random processes, or I mean, it could have some similarities. Those random processes can have some similarities, but we are going to find the we are going to find the we are going to compare and we are going to find any kind of similarities between two or three, multiple different random processes, right? So, uh, so basically the joint behavior of uh, right? So the joint behavior of random processes we are going to consider. The joint behavior of random processes we are going to consider here. So when we are using this, when we are trying to define that, we will be using some parameters that are basically um, uh, cross correlation. We'll be using cross correlation function and the cross covariance function, right? So you can remember earlier we talked about the autocorrelation function. Right? Autocorrelation function, then we learned about the autocovariance function. So this word auto was used earlier, right? So in that case, we discussed about two time instances in the same random processes. Two time instances in the same random process, we discussed and we compared those things, right? So in the case where we consider the same process, same random process, we call that we call those statistics as autocorrelation and autocovariance. If we are considering cross correlation and cross covariance, that means we are going to consider two time instances of two different random processes or two different signals, right? Two time instances of two different signals or processes, we can say, right? Signals, right? So if we are going to compare two different signals and then we are going to compare the time instances, the variables that related to those time instances, uh, if you are going to compare the random variables related to two time instances of two different random signals, we call that uh, we call those statistics as cross correlation and cross covariance. So cross means different random signals are considered. So based on that, we can define the mathematical functions for these two parameters. So if we take the parameters, mathematical parameters that we are considering here, the autocorrelation function, right? The cross correlation function, cross correlation function is given by the integration of autocorrelation. Just like autocorrelation, we can find the cross correlation. The only difference here is that the cross correlation can be found by taking the correlation between X and Y signals, right? If you take, there are two signals at T1 and T2 time instances, we are going to study these two signals, and that is defined as the expectation of xt1 and yt2. So this y is a different signal to the different to x signal. This y signal is a different signal to x signal, right? Apart from its difference, the time instance at where we are comparing these two signals is also uh, like a different time instance, right? So maybe, right? So if you have any questions, you can ask, right? So we are comparing two signals with two different time instances. That one, so the time instances are defined by T1 and T2. So let's assume we know the values of the time instances And then we are going to compare these two signals X and Y related to those time instances. So those specific time instances. And cross covariance function. And apart from that, one thing to note is that if, for example, if at some point the correlation function Rxy is 0, right, for all the T1 and T2 time instances, right? So this symbol means for all time instances, right? So for all time instances T1 and T2, if we can observe that this cross correlation uh, uh, is equal to 0, that means that the product that we obtain here, right? This product basically EXT1 into YT2 is equal to 0, which means that XT1 and XT2 are orthogonal signals, right? In the earlier classes, we learned about the orthogonality of random variables, and orthogonality of random variables occurred when the expectation of the uh, random variables product is equal to 0. So if this is happening, right, if this is the case, right, so if this is the case, then we can say the xt1 and xt2, sorry, uh, the xt1 and yt2 are orthogonal. xt1 and yt2 are orthogonal, right? So actually now if it is happening for all the time instances, we can say basically that xt random process and the yt random process are orthogonal. So basically these two random processes xt and the yt will be basically orthogonal. So that orthogonality applies to all the time instances. So therefore we can generally write t in here rather than writing t1, t2, something specific. We can write t as the common variable. So basically for any time instance xt, it will be orthogonal with the yt signal. So that is basically with regard to the orthogonal random processes, right? So in the last class, we discussed about different random processes, and we discussed up to the point of talking about uncorrelated random processes. And in this point, I think we discussed about the orthogonal random processes and its definition. So this is the definition of the orthogonal random processes, and this this is also another type of random process, right? So far I think we discussed about multiple random processes. Anyway, right, in I will discuss about this orthogonal random process again. So anyway, we were discussing about the cross correlation function, and now we are going to proceed to the cross covariance function. And before doing that, I will say that cross correlation function is not symmetric, right? So there's another condition saying that this cross correlation function is not symmetric all the time. So which means that uh, now cross correlation function is defined as the rxy rxy t1 comma t2 equals ex t1 product yt2. So in this case, for the autocorrelation case, right? For autocorrelation case, uh, it is for autocorrelation case, it is um, it is the theory that the for any kind of real processes, the product between these variables is reversible, or we can see symmetry in those two random variables. What I mean is that for autocorrelation function, if the process is a real process, which means it is not a complex process, right? That means that the random variables are not complex, right? So not a complex process. And if that is the case, if the random variables are real all the time, we can say that the autocorrelation function is a symmetric function, right? We can say the autocorrelation function is a symmetric function if the process is a real process, or else what I mean is that the variables are real variables, which means that they are not complex random variables. If the autocorrelation function is symmetric, what it means is that the xt1 and xt2, right? If we take autocorrelation, it should be the same signal that we are considering, and the xt1 and xt2 are interchangeable. The values of xt1, xt2, the order of doing the multiplication can be interchanged, right? So which means that we can say that ext1, ext2 are equal to ext2 and ext1. However, in the cross correlation case, it might not be the same thing. So this order can be reversed, right? This order can be reversed, and if it can be reversed, it is a symmetric process. xt1, xt2's expectation equals the expectation of xt2 into xt1. Apart from that, now we were talking about the cross correlation function before, and for the cross correlation function, this theory will not apply as it is. So, which means that if we are observing these two different random signals, then this expectation operation that we apply on these two different signals might not be equal to the uh, yt2 xt2 all the time, right? not not equal all the time, right? So not satisfied all the time. So which means that not symmetric all the time, which means that the cross correlation function is not symmetric all the time. There could be instances where it is symmetric, but there are some instances where the cross correlation function is not symmetric. So with related to the symmetry, that is about it. Then with related to the other statistic, which is the cross covariance, now we have to discuss about the cross covariance. So we were discussing about multiple random variables, and we were discussing about the cross correlation statistic. Now we are going to discuss about this cross covariance. So the cross covariance is defined um, as the difference between I will show using mathematical equations. So cross covariance is defined. We can define it using this expression. I will use these notations to define the covariance. Okay, so basically COV. If I'm going to take the covariance between x and y signals at time instances t1 and t2, I will denote it as COV xy t1 t2. Then it can be defined using expectation operations like this. So basically, we are going to find out the covariance between xt1 and yt2. So xt1 is one signal we are going to compare with, and since we are going to find the covariance, we have to take the mu, or we have to take the um, right difference between the random variable and the mu value of the random variable, mean value of the random variable. Then we need to take the product of this term with the random variable yt2. So yt2 also has its own mu value, or the average value, where yt2 is having an average value of mu y t2 at t2. And this entire product we call as the value that is giving the cross covariance value. The cross covariance value is defined, further by simplifying this, we can define that it is equal to Rxy T1, T2, which means that the cross correlation between T1, T2 random variables of X and Y minus the mu value of the random variables at T1 and T2 and their product, basically. So we can show this as a solution to right. So you can try this on your own and see whether this equation is satisfied. We have discussed about similar examples or similar theories in the last week classes. So I believe that you should be able to derive this output if you are asked to derive the cross covariance equation starting from the fundamental theories. Then right. So if in some case, the cross covariance value is equal to 0, right? If in some case the cross covariance value is equal to 0, then that means that Rxy T1 T2 equals mu T1 mu y T2. So if the cross covariance value is 0, this equation becomes 0, right? So this equation A becomes 0, which means that the autocorrelation function equals the expectation values of mu T1 and T2. So that means that Rxy T1 T2 equals mu X T1 mu Y T2, which means that these two processes, X and Y, at time instances T1 and T2, uh, is are uncorrelated, right? So if this property is satisfied for all the T1, T2 time instances, right? So if this property is satisfied for all the T1, T2 processes, right? Satisfied for all T1, T2 time instances, sorry, for all the T1, T2 time instances, then we can call that X and Y random processes are basically uncorrelated. So XT and YT are uncorrelated if this condition is satisfied for all the T1, T2 values. So XT and YT are uncorrelated. So if they are uncorrelated, we can simplify the autocorrelation function as the product of the expectation of the xt1 variable into the expectation of the yt2 variable. So we discussed up to that point about the um, independent processes, orthogonal processes, uncorrelated processes. And so with regard to independent processes, there are two processes that are independent, right? If there are two processes that are independent, right? Independent, then we can say that for sure those two processes are uncorrelated. However, if they are uncorrelated, we cannot ensure that they are independent, right? So the reverse might not be always true. right? The reverse may not always be true. So if we take an example for this, for independent random processes, an example would be the communication example, where we can consider some kind of independent random processes occurring, right? So if we take an example, one example would be, right? One example would be the case where we receive a signal plus where we receive a signal which has a combination of signal, desired signal and noise signal, right? If we receive a signal which is we receive a signal which is y under the presence of x and noise, under x signal which is the desired signal and noise, noise signal, right? So in this is basically, this can be basically represented as y equals x plus n, which means that this means that this x is the desired signal, and once this desired signal is received at a certain point, um, that received signal is given by y. Okay, so the received signal is given by y, and this noise signal is another different signal which is getting added to the desired signal. So these x and noise signals are independent processes. X and n are independent processes or independent signals. So they are independent signals. So therefore, when we are studying the mathematical, I mean, probability density functions, and when we are studying the probability density distributions, and when we are studying the statistics of these of the output signal that we receive, then we can consider these two processes as independent random processes. And once we consider that, then our computations becomes relatively easy due to that assumption. So with regard to multiple random processes, that's about it. And we have discussed about basically important statistics such as cross correlation and cross covariance. So these two characteristics are always appearing in multiple places, and therefore these terms must be very easy or very familiar to you when you are studying this signal processing domain applications. I mean, domain, any kind of work related to signal processing. I think it's better that we are more familiar with the statistics such as cross covariance, cross correlation, and so on. So if you have any questions up to this point, please let me know. Right? So So I think we can discuss about the kind of the summary we have discussed so far. So the random processes we have considered, uh, and we have considered about, I mean, the single random process, and we have discussed about the multiple random processes, right? So when we consider about the single random process, um, we discussed about the expectation value of the process, or the mean value of the random process. We discussed about the variance, or else the variance of the random process, and we discussed about the mathematical definitions of the random process which is occurring at, let's say, xt1, or some kind of a time instance xt. So uh, for all those properties we mathematically define the functions, right? Thirdly, we have this auto correlation function that we define, which we define for the single random process, right? In the last class I discussed about this auto correlation part, right? So in addition to what I discussed in the autocorrelation, I would like to mention something else, or something additional to what I discussed in the last class, which means that I will give some more definitions related to the statistical, definition of the autocorrelation function. So the autocorrelation function we defined as Rxx, T1, T2, right? Rxx T1, T2, and this one we defined as, we can define this autocorrelation, right? Autocorrelation as uh, the expectation of the random variable xt1 and xt2. So in cases where we have random processes um, which are basically IID, we have certain specific uh, properties. If the random process is IID, then its expectation, its autocorrelation value equals to expectation of the random variable. Uh, uh, I will denote that mathematically, right? So autocorrelation function we can define for the the IID random processes, independently identically distributed random processes, and these random processes basically have the same, um, right? The feature of these IID processes is that the same PDF is there for all the random variables, right? For all the random variables at xt1, t2, t3, likewise. So for this kind of a IID process, the autocorrelation function can be defined as uh, uh, the autocorrelation function can be defined uh, as a value which is equal to uh, so the autocorrelation function can be defined like in general using this definition, where if the T1 value is equal to T2, let's say they are different first, they are different, then the values of this autocorrelation will be the product between these two random variables. So the product between ext1 and ext2 can be taken. So singular product between the expectation or the mean value, singular product of the mean value of xt1 and xt2 can be taken as the autocorrelation value once t1 and t2 are equal. Sorry, not equal. They are equal. It should be that the final output will be equal to the value of the autocorrelation plus the variance of the random variable. So it comes using mathematics. So maybe you can look into it later. So if this is not clear or if it is not coming to you once you try to process, then you can let me know. So this sigma function is also added once we are taking the xt1 variable and finding the autocorrelation at the same point. Right, at the same point, if you are trying to find the autocorrelation, then we can find the value as this, which means that the autocorrelation of a signal at the same point is very high than the autocorrelation that we can observe at two different time points, which means that this value is added, which shows that the similarity between the same time instance is very high. Should be the case, right? It should be the case if you can understand me, right? So if we have a certain random signal, which looks like this, we are trying to analyze the correlation between two time instances. If you are trying to study the correlation between two time instances in this random signal, right? The highest similarity will occur at the same place. It is a very random signal. If we take, for example, this point, right? This point t1, which is equal to 1 second, let's say. And if we try to find the autocorrelation between t1 1 second and again t1 1 second, then the autocorrelation will be the highest in this point, which means that the similarity between this point and again this point will be the highest. Whereas when we take the autocorrelation between t1 and t2, which are two different time instances, let's say t2 is 5 seconds, then the similarity between these 2 points is very low. So the similarity is low when we are considering two different time instances. And that is depicted in here. And the similarity is very high, and the time instances are they are equal. The same time instance is considered when we calculate the autocorrelation. So those are the mathematical definitions of the autocorrelation function when the process is IID process. And if we take again the uncorrelated process, similar behavior is seen for the uncorrelated process. And also when we take the autocovariance, right? So if we take autocovariance, right? We take a autocovariance, which I will denote using COV, autocovariance of the same signal at time instances T1 and T2. The autocovariance value will be equal to 0 if the uh, time instances are not equal, which means that the time instances are not equal, and if the if they are yeah, so if the time instances are not equal, the covariance function, which we can define as the expectation of xt1 minus the mu t1 into right? So if T1 and T2 are not same, then and the autocovariance function is the highest when the signals are similar, right? So if they are not similar, if these two signals are not similar, then these two signals have zero covariance between them. And that is why we get zero here, where once you take the expectation and once you get the uh, once you get the uh, autocorrelation function from here, and then so like, right, so this condition, right, where we have the covariance equal to 0 happens where these xt1 and xt2 are uncorrelated. So we learned that for uncorrelated cases, this this autocorrelation is equal to the product between these uh, two variables and their expectation values. So this function, this covariance function, is equal to 0 when xt1 and xt2 are uncorrelated, right? So when xt1 and xt2 are uncorrelated and when they are independent, right? They are independent, or if they are uncorrelated, we can see that the autocovariance function equal to 0. So maybe you can search about it, and if it is not clear to you, you can let me know. We already know the definition of covariance, and the covariance function equal to 0 at the place where the variables that we consider xt1, xt2 are independent. They are independent, then the value of covariance will be equal to 0. Then if we take the same time instance, if we consider the same time instance, uh, T1 and T2, right? By equating T1 and T2, we can get the same time instance, and we can compute the covariance of the same time instance. So the same at the same time instance, the covariance value will be equal to sigma squared x T1. So that also you can try to figure by the definition of the covariance, and you can try to get these two values for the covariance under these two conditions. So this is the mathematical definition of the covariance, autocovariance under IID random processes, right? And that is valid, and that these two properties of autocorrelation and the autocovariance are also valid for the so for uncorrelated cases as well. So for so you can consider these things and you can see whether these two characteristics are satisfied for the IID process. So up to that point, I think I have done mathematical definitions of the different processes. Apart from that, I would like to discuss about the orthogonal case, orthogonal random processes case. And orthogonal random processes are processes where the product between the two random variables uh, and its expectation value equals to 0. So if so for orthogonal random processes, right? If you are taking the same random process, right? If you are considering the same random process, I will say that we are considering the orthogonal random processes, right? So in here, we were discussing about single random processes. Under that, we were discussing about the mean, variance, autocorrelation. And under autocorrelation, we discussed about the IID processes, and we discussed about how its autocorrelation function works, right? And then we discussed about the covariance function also of the IID process, where the covariance process has values of 0 if time is not equal, and it has a sigma, or it has a certain value when the time instance is equal, or when we are considering the same time instances of the sign of the signal. So the covariance function is like that. And then for random processes which are orthogonal, right? For random processes which are orthogonal, we can define that the orthogonal random processes have a value of orthogonal random processes autocorrelation function value has these values has a value of 0 if the time instances are not equal, which means that there's no similarity between time instance T1 and T2. And if the time instances are same, there is a value which is equal to the square of the mean value of the random variable xt1. So if it is a random process which is orthogonal, we can define the orthogonal, right? We can define the values of the properties using its autocorrelation function. So autocorrelation function is very useful, therefore, to find the properties of the process. So if you are asked whether a certain process is orthogonal, you need to find the autocorrelation function. Then if right, so if a certain process, right, if a certain process is zero mean, it is both orthogonal and uncorrelated because the autocorrelation function equals the covariance function, right? So there's another like a concept that you can remember for all the random processes in general. I will write that later, but now I will discuss about the multiple random processes that we discussed about. So we discussed about the cross correlation property and we discussed about the cross covariance property. We define the cross correlation definition and the cross covariance. The only difference when you consider the single process in the multiple process is the case where we are considering two different signals or two different independent random two different processes. Then we are comparing the statistics of those two different processes. That is why we are calling these statistics cross covariance and cross correlation. So for any process, if we find that if a certain process is right, if we find that a certain process is uh, orthogonal, right, if we find a certain process is orthogonal and uncorrelated, right, by definition, right, if a random process is both uh, orthogonal and uncorrelated, right, if they are both orthogonal and uncorrelated, we can say that it is sorry, I mean, if a random process is zero mean, that means if the random process has mu equals 0, then it will show that the process is both orthogonal and uncorrelated, right? So for us to check the orthogonality and uncorrelatedness, we use the RxX value, right? Or the autocorrelation value. Autocorrelation value for any time instances, T1 and T2, is defined using the expectation operation of xt1 and xt2, right? So expectation operation of xt1 and xt2 we use, and if the random process is having zero mean, that means that this process is basically having um, the mean as 0. So uh, right, so the autocorrelation function we can define like this with the product. And for covariance function we can define for T1 and T2 as the autocorrelation function uh, minus the product of the mean values, right? So mean values xt1 and xt2. Mu T1, mu T2, I will say. So both are related to the X variable. And if the means are 0, that means this part is 0, which means that the autocorrelation function is equal to the covariance function, right? So these two expressions are equal in case where the mean value of the random process is 0, right? So if these are like, yeah, if these are equal, right? If these are equal, uh, that means that the, right, if for these two to be equal, the um the expressions of autocorrelation, um, yeah, so if they are 0 mean, we can further, further deduce that the the by definition of the covariance, by definition of the covariance, right, which is equal to x minus mu t1 multiplied with x minus mu t2. So due to 0 mean these two values are going to be 0. If that is going to be 0, it is the covariance is going to be the product between xt1 and xt2. Right? So apart from that, if the process is 0 mean, we can say that the product between the expectations, right? The product between the expectations also equal to 0, right? Because of the 0 mean property, singularly, if we take these values xt1 and xt2, we multiply those things, we can get 0, which means that the product between the two expectations equal to 0, which means that the process is uncorrelated and the process is also like orthogonal. So you can look into this factor furthermore, and you can check whether it's true. If it is not true, we can discuss about it, right? So since the 0 mean property is there, the singularly we can say expectation value of the random variables are 0 singularly. So if we take the product of those two random variables and then take the product, they are going to be equal to 0. And if the two products are like separately taken like this, and those products are 0, then basically the that case we refer to orthogonal case. And also it shows that there's no relationship between xt1 variable and xt2. And if that occurs, then xt1, xt2 are uncorrelated. So I think with that orthogonal processes, I think I have discussed. So apart from that, right, we started discussing about something called stationary processes in the last class. Okay, so we have discussed about several random processes. So I know that all these processes, they are definitions, there are so many definitions, right? So we discussed about random processes, we discussed about single random process, multiple random process. And so under each those processes also we discussed about different statistics or different mathematical functions that can define the mean value, variance value, autocorrelation value, cross correlation value. Likewise, for multiple case, we discussed about the cross correlation, cross covariance case. Uh, the the functions that define the cross correlation and cross covariance. So these things we discussed regarding the random process. So I mean there are so other things also that we discussed about the random process, different types of processes we discussed, right? So when we discuss the type of processes, we discussed about the independent random processes, then IID random processes, which is the independent and identically distributed random processes. Then we discussed about uncorrelated random processes. Then we discussed about the orthogonal random processes. And lastly, we are going to talk about the stationary random processes. The stationary random processes. So stationary random process are like they have their own different definitions. So stationary random process is something that we have to separately consider. So stationary random processes I can divide into basically two types. One thing is known as the strict sense stationary processes. So I can divide the stationary random processes into strict sense stationary and wide sense stationary, right? So we will discuss about the strict sense stationary first. We give a small, like definition about this strict sense stationary process. And then if we have the time, we will discuss in detail regarding the strict sense stationary processes. So the strict sense stationary processes are basically processes that have statistical characteristics that are constant at each time instance, right? So I will first write the definition here, and then I will explain using some, graphs or plotting, some kind of visual plots. Basically, the statistical parameters of a stationary process is not changing over time. So statistical characteristic will remain constant over time. Will remain constant over time, right? Remain constant over time, right? Remain constant over time, uh, right? So strict sense stationary process, the statistics that we consider here, we consider statistics up to the nth order in here, right? So basically, the statistics are not affected by any shift in time. Statistics are not affected by shifts in time, right? The statistics are not affected by shift in the time origin, shifts in the time, right? So this thing we will discuss further, right? And in contrast, we have these wide sense stationary processes. These wide sense stationary processes are where the statistics remain constant after the second order parameters, right? The statistical properties remain constant. Uh, stat Statistical properties remain constant up to the second order, right? Up to the second order characteristics or second order parameters. Okay. So up to the second order parameters, these statistical properties will remain constant. So that is the main difference between the strict sense stationary and the wide sense stationary, right? So wide sense stationary process is a simplified version of the strict sensation stationary process, right? Strict sense stationary, the word strict means that up to nth order, all the statistics are same, right? So this is kind of a very strict kind of a, definition where all the statistics must be same in all the time variables, right? In here, however, wide sense stationary means a lesser, lesser complex or lesser strict definition, where this wide sense stationary definition is valid only for statistical properties up to the second order. We can say there's the mean value and the variance value are same. Mean value, variance value, autocorrelation value, autocovariance value. Those statistics are constant uh, for this random process over the, you know over the time. But this wide sense stationary process might not have these uh, other higher order statistics same at each time variables, right? So that is basically the difference between the wide sense stationary and the strict sense stationary process, right? So we will discuss about this further, but now I'm hoping to give that quiz that I'm hoping to give. So, right? So, in order to do that, uh, I will ask you to join to a certain platform, right? So, in 5 minutes time, we will start the quiz, right? So let me, give you, so I will share that. So in 5 minutes time, you can join that quiz. If you have any questions, you can ask. Okay. So are you ready? So some student asked whether this carry some marks. Well, actually, this is carrying some bonus marks. About like bonus marks means maximum 3 marks out of the quizzes that I'm conducting during the lectures, right? So I mean, for the final grade, this bonus marks out of 3 will be added. That is all that is happening. So it's not a big, huge impact on your final grade, but maybe you will have some points, right? So the assignments that are defined in the module outline are the ones that are defined for this module, right? So you can do some assignments that are basically 5 assignments, right? As defined in the module outline. We will do the assignments as defined in the module outline. But apart from those marks, these quizzes will carry some bonus marks. So for the students who are attending the lectures, they will get that. And so if you don't face the quiz today, don't ask me to repeat this because this is only for today and you will get that as a bonus mark. So it is not the standard mark that is defined for the continuous assessments. Is that clear? So actually, this is a fun activity, I hope, right? It's not a serious one. So I want you to join to a website called Kahoot, right? I will share the screen now, and you need to join to like a Kahoot quiz session, right? So you have to go to kahoot.com, right? Kahoot.com. Right, I will just try to. You can go to Kahoot, and you can, once you go to kahoot.it, you can put the game pin, right? So go to that link. I will put the link. Then you can. So this this game pin, you can put the game pin, right? So, and also when you are logging into this, you will be asked to put your name. Put your name plus the registration number of yours, right? I need to check the registration number and also your name. And then based on that, I will give the marks. Okay. So put this game pin and put the ID and your number, your name as the name of your name, right? So I'm waiting for you to join this. Once you join, I will start the quiz. Okay. If possible, put your name as well. Just first name. Pin number is this one, 5663894.
Pin number mean password?
This one. You can see in the screen, right? 5663894.
Yeah, this is okay, but I'm trying to log. So in login. Okay, is it kahoot.com, no?
Kahoot.it actually.
Okay.
You can find the link in the chat. I have put it there if you want.
Yeah.
So put your registration number and your name if possible, if there's enough space there. I think there are 19 students, 20. So I'm waiting for all of you to join. Individually, you will be competing here, right? This is actually a game. I will give you 5 minutes maybe to join. Any
I'm already
questions?
joined, madam.
You're
I'm
not
already joined.
shown here.
No, I shown that.
Okay, then fine,
PC
great.
PC
Okay,
332
23. Okay, then it's
23, no?
fine. Yes, then you are joined. I'm waiting for 5 more students. If possible, join, or else are you not joining? I will start the quiz now. I'm waiting for the rest of the students to join. So I think now the time is up. I think those students may not be joining. I will start. The other students, you can start, putting the answers, selecting the answers, right? So I will start. So this is a game. You can play it as game. So if two random variables x and y are independent, they are uncorrelated. Is it true or false? Okay, so only 4 students have given the answer. So you have to give the answer very quickly. Otherwise, your mark will not be taken into consideration. So these students have got the marks with these ID numbers. So they have got the marks, and you have to give the answer within the limited time, right? So next, if two random variables are uncorrelated, they must be independent. Is this true or false? Okay, so if there are two random variables which are uncorrelated, they are not all the time independent, right? So I have discussed this previously, that there could be some nonlinear relationship between the two random variables. So because of that nonlinear relationship, they are not independent. So therefore, this expression, this fact is false. It's wrong, right? So the students who got it wrong, that means students who selected true, you need to consider this part, right? You need to rethink. So yeah, so the first place remains the same. So let's go ahead. What does the term ensemble refer to in the context of random processes? Single outcome observation of random process, the set of all possible outcomes or observations of a random process. Thirdly, the mean of a random variable or the variance of a random variable. Right. So the ensemble, I think we discussed, is the set of all the possible outcomes of a random process. Right. So the all the possible realizations of the random process is the ensemble. Right. I think we discussed that in our diagrams, right, about the random process. I have shown you what the ensemble is, and the ensemble can be, ensemble can be studied by studying one time instance of the random process, right? You can consider specific time instances of the random process to study the ensemble, right? We have ensemble mean, ensemble variance, and likewise, different statistics can be defined on top of the ensemble, right? For the ensemble, we can define all the statistics, mean, variance, autocorrelation, likewise. Okay, so let's see. Now, yeah, the first person still is in the lead, right? So let's move ahead. A random process can be categorized as either continuous or discrete based on the nature of the outcomes it produces. Is this true or false? Yeah, so a lot of students have scored the correct answer. So yes, it is true. So you can categorize random processes as either discrete random processes and continuous random processes, right? So random processes, if the outcomes of the random process have discrete sequences, then those are discrete random processes. And if the outcomes are continuous sequences, then those random processes are continuous random processes, right? If these are not clear, or something that if there are something that you cannot understand, you can let me know in the chat, or you can speak up. Okay, so yes, 23 PG1003 still in the lead. So we will see how it goes. What does the term realization refer to in the context of random processes? The set of all possible outcomes, a specific outcome or observation from a random process, average of all outcomes, or the mathematical function described in the process. You need to select the most clear, most clear answer, right? Most clear answer, which is the second one. So the specific outcome of a random process we call as the realization. One specific outcome is known as the realization. Right. So I think we discussed that in the class using the figures for the random process. Okay, so we can see that, yeah, we can see that the scoreboard remains a little bit the same. Let's go ahead. The sum of probabilities of all possible outcomes of a random experiment is equal to 1. Is this true or false? It is true, right? The basically from the probability theory, the sum of all probabilities uh, uh, of a certain random process or certain random experiment uh, is equal to 1. The sum of probabilities of all the outcomes of a certain random experiment equals to 1. That is the basic theory related to the probability of a certain event. Okay, so we can see the scoreboard remains a little bit different now, but the lead is still the same. Yeah. Probability mass function TMF is defined only for discrete random variables. Is this true or false? Yes. So probability mass function is the distribution function that is defined only for the discrete random variables, where we define this mass function as the summation of the random variable into of the as a summation of the probabilities. Or if we want to find the value of the probability of a certain event occurring under discrete random variables, we need to take the summation of all the probabilities under the discrete random variable values. So the probability mass function is defined for discrete random variables, right? For discrete time or discrete random variables only, the mass function is defined. So the continuous version is the probability density function, basically. Okay, so let's go ahead. I think some scores have changed. The mean of the Gaussian distribution represents the center or average value of the random value distribution. Is this true or false? I think this is pretty easy question. So the mean value gives the center value of the distribution of the random variables. So for a Gaussian distribution, it is at the center of the random variable distribution. So it should be true. Almost all of you have taken the correct answer. Only 3 incorrect answers are there. So still the lead remains the same and the scoreboard has not that changed much. And if a sequence of independent and identically distributed random variables, they will not be uncorrelated. Right? If there's a sequence of IID random variables, they will not be uncorrelated. That's what they are asking. So is it true or false? So yes. So actually the correct so the correct answer is false, right? So if the process is having identically independent and identically distributed random variables, which means that they are independent. Those random variables are independent. So if they are independent, that means those random variables are uncorrelated. In here, I'm asking whether it is not uncorrelated. So which means that it's not true, which means it's false. Is it not clear? Do you have any questions on that? right? I'm not asking whether they are uncorrelated, but I'm saying it is not uncorrelated, which means that I'm saying that these random variables are correlated, which means that these identically distributed ones are correlated, which is wrong. So this statement is wrong. So there's a trick in the words in that question, but it should be visible to you. I have like capitalized or highlighted not. So next question, the last one. How is the ensemble average of a random process at a specific time t calculated? Taking the average over different time instances, taking the average over all possible realizations at that specific time, considering the maximum value at that time, and considering the minimum value at that time. Correct. So most have got the correct answer. So the ensemble average means taking the average of all the possible realizations at a specific time instance. So ensemble average means that you're considering a specific time instance, and then you're averaging out the values of the variable at that time instance. So I think that's all. I think we will see, yeah, there are first three places, and we can see like these three people have got the places. So I think it's really good. So you have scored some good marks. So anyway, I will put the marks of all these, results by all the people in the LMS. So I hope that you have access to the LMS, and I will post the results that you have got in the LMS. So thank you for joining, and I will be able to get the results out of this software, and later I will publish that. If you have any questions related to the quiz, and yeah, if you have something to clarify, you can ask. So you can have maybe a certain maybe time, maybe break of 5 minutes, and we will start about the strict sense stationary processes, and we will discuss some things related to those strict sense stationary processes.
Madam, can you share that quick for chat LMS?
Sorry, in LMS I will.
Yeah, can you be able to share that quick 10 quicks for LMS?
You mean what, the questions?
Yeah, quicks.
Yeah, questions and answers I will share.
Okay.
No problem. Okay, so I think I will discuss about this the next parts of the of the theories that we have discussed. So we discussed about the stationary random processes, and there are two main types: strict sense stationary and wide sense stationary. When we talk about the strict sense stationary, they are kind of strict processes which are not that much available in the real world. This is used for kind of like theoretical assumptions, and uh, not really not for real world applications. So there are like there are many random processes, but most are not strict sense stationary processes. So this definition is basically based purely for theoretical understanding about the strict sense stationary processes. So there are not much of real world applications of this type of random processes. Not much of real world applications. Right? There are not much of real world applications, and therefore strict sense stationary processes are not really practical, but these are used to give a basic definition of what strict sense stationary means. When we talk about the parameters of these random processes, the statistics, as I said before, will remain unaffected by the shifts in the time origin. So we will discuss about the shifts in the time domain, right? So which means that if there's a certain random process, right? If there's a certain random process that gives out random outputs, right? So this we will take that these outcomes come from a certain random experiment. So this random experiment, right? This random experiment will give out outcomes related to the time domain, right? And it can be time domain or spatial domain. For the moment, we will take with respect to time domain, right? For easiness of understanding. So these time domain sequences will have certain values over the time, different time instances. And since this is a random process, the values will be random, and the values will change very fast over the time. So the same pattern will not occur all the time. So peaks can occur at different time instances than the other random sequences. So these outcomes we call as realizations. So this is realization 1, realization 2. Likewise, we have different realizations for a random process. So there could be n number of realizations. So the number of realization will depend on the certain random process. We cannot specify the number of realizations to be infinite amount or finite amount. We can say that it will depend on the application, right? So the realization number 3 will also have its own output with respect to the time. So if I draw these time sequences in an aligned manner, I can see that we can observe the time instances, and we can observe the variable, right? Random variable with respect to the time instance. Let's say time t1 or something. Let's say it is equal to 1 second. All right, so time equal to 1 second for all the sequences we will consider, right? And then we take another time instance, let's say time equals 7 seconds or 5 seconds, something else. So if we take the characteristics of the sequence at the 7 time second, right? 7 second, then we can have different parameters or statistics related to that time instance. So if in a case these two, parameters are equal, right? So if the probability density function observed here is equal to the probability density function seen here, for example, let's say this is Rayleigh distributed and this is also Rayleigh distributed, then we can say if this pattern exists for all the time instances of this sequence, then we can say that uh, in such a case, this entire random process that we consider, right, this random process that is defined by all these realizations will be a strict sense stationary process, right? If the statistics of um, the random process at right, if the statistics of the random process of the random process for all time instances, right? For all time instances, t1, t2, up to tn, whatever the final t value, all the time instances, the statistics will remain constant, right? Will remain constant, right? So if you can't understand, you can ask. Statistics will remain constant. Statistics will remain constant. So what are the statistics? The statistics that we consider here are basically the mean, let's say, variance. Then we have autocorrelation. Autocorrelation. If we are taking since we are taking the same random process into account, we will consider autocorrelation and then autocovariance. There are also other nth order statistics, other nth order statistics also. This nth order statistics also that we can compute for this random process will be constant at each time instance in this sequence. For each time instance, let's say t equals 1 second, t equals 7 seconds, t equals 100 seconds, t equals 1000 seconds. For all the time instances, the statistics defined on those time instances will be same, right? Which means that the PDF function will be same for all the time instances, right? So that means that the mean value will also be same. Variance will also be same at each random variable. So this statistics being same for all time instances is the characteristic of the strict sense stationary. Moreover, it is same, it is valid for up to nth order statistics. So if you are going to mathematically represent the conditions or the characteristics of a strict sense stationary process, the expectation value or the mean value of the random variables xt1 is going to be equal to xt2, right? So xt1, xt2 are random variables which are defined for the time instance t1. This is defined for time instance t1. This is defined for time instance t2. So the random variables mean value defined for t1 time instance is equal to the random variables mean value defined for the time t2. So these are going to be equal to a certain constant mu value. Apart from that, when we take the sigma value or the variance will also be equal at xt1 and xt2. So I'm going to represent the variance as using this notation, sigma squared subscript capital X and then t1 equal to sigma squared at t2. This is also going to be equal to a certain constant variance, sigma squared. Then when we take autocorrelation, right, autocorrelation is also constant over the time, right? However, it doesn't mean that it doesn't vary on any kind of a time value, right? So in here, I will explain the autocorrelation value between T1, T2 variables will be equal to the autocorrelation function, which is depending on the like, let's say I will first write this one and I will show you that now the autocorrelation between T1, T2 time variables is equal to the autocorrelation which can be obtained at time instances T1 plus epsilon, comma T2 plus epsilon. In that case, what we can see is the same time instance is there in both these two expressions. The only difference that we can see with the time instances considered in this second autocorrelation is that all the time instances have been shifted by a certain specific time duration of epsilon. So for both time instances, we have added epsilon, and once we are adding those time duration of epsilon, the autocorrelation value has not changed, right? So which means that autocorrelation value between 2 points rely only on this time delay that we have introduced. The autocorrelation value is same, but it is only relying on this time delay value. So therefore, autocorrelation value is not dependent on the variable's time value. This does not have any impact on the final autocorrelation value that we can obtain. The specific instances of the time t1, t2 does not affect, but this epsilon value affects. So most of the time we put this delay as tau, right? So in mathematical books and in all the definitions, we can see that this time shift that has been added is denoted using some tau value. So we can say that autocorrelation value depends on the tau value or the time delay uh, that we can apply compared to the other signal. So actually, what I say here is actually, I think I need to explain it a bit further. So in here, this autocorrelation values depends on the time delay between these T1, T2 time variables. So the time delay between T1, T2 is given using tau, right? So whatever the time delay between these two time variables, we define using tau. So tau is a constant value that that is defined. So this tau value is not a variable. Because of that, this autocorrelation value is constant for any time instance in the random process, and therefore the autocorrelation value is remaining same at each time instance of the random process. So you can actually think about this when you have some free time. So it's not easy to like understand. Maybe if you're learning this for the first time, you might not be able to get it understandably when you first learn it. So you need to refer some of the materials we have discussed, and you can refer in the Google, and then you can try to understand how this autocorrelation function is defined in this manner. So we discussed about the strict sense stationary process, right? So as I said before, the strict sense stationary processes are not that practical, right? Not that practical in the real world, right? Although it's a theoretical assumption, it is not sufficient to model the real world applications. So in order for us to model the real world applications, we are using a lesser complex, lesser strict uh, version. So strict sense stationary processes are not sufficient to model the real world applications. In order to do that, we are defining a lesser strict version, which is the wide sense stationary processes. So the wide sense stationary processes are processes that are less strict than the strict sense stationary. And in there, the special feature is that after the second order, the statistics are defined, and statistics are constant after the second order in the random process. So that also we will look at, and then we will be able to discuss about the differences between the wide sense stationary and strict sense stationary. If you have any questions up to this point, please let me know. So the wide sense stationary processes have the statistical properties constant up to the second order, right? So up to the second order, the statistics are constant. Then when we talk about the mathematical definitions of such processes, wide sense stationary processes, so the second order parameters that we can consider are like, for example, the mu value. So the mu value is constant over all time instances. So the mu value is constant over all time instances. Therefore, we can say that the expectation value will be same and it will be equal to a certain constant mu value. So we can say xt, right? Expectation of xt equals to mu. Any for all time instances, t1, t2, t3 likewise. So for all the time instances, the mu value that we can obtain will be same, right? So I think we discussed using this diagram earlier also. If you want to look at it, you can look. So in here, this time instance t equals time 1 second and 7 seconds. If we compare the mean value that we can obtain uh, of the random variable will be same, right? The probability density functions will be same, and the mean value that we can compute for that time variable will be same, and it will be like that for all the time instance. Similarly, the variance value, or the next we will consider about the autocorrelation value, right? Variance value will also be same, and if we talk about the um, I will take the variance value. Variance value of xt1 or xt will be same as some kind of a variable, some kind of a sigma value, sigma squared. Right, so sigma squared represents the variance function, sigma squared. So when we take any time instance, it will be satisfied, right? T1, T2, T3, any time instance, this expression will be satisfied, which means that sigma value, sigma squared value for any time instance T1, T2, 3 will be equal to the sigma squared. And then once you take the auto correlation value, when we take the auto correlation value, right? Auto correlation value, right? T1, T2, right? Right, right. So then we can take that autocorrelation will be equal to a value which is determined by this tau value, right? It doesn't depend on the T1, T2s, but it depends on the tau value, basically. And then autocovariance, right? Autocovariance value is defined. Uh, I think we defined this earlier as well, which is defined by the difference between autocorrelation value, right? Autocorrelation value that we can define, right? So when we are writing the autocorrelation value, we can write two x values in here, right? To show that there are two signals that are in consideration. And autocovariance expression will be the difference between rxx tau minus the mu value, right? Mu value of the specific time, or a mu value will be same for all the time instances, and therefore it is a constant value. So it will be mu xt. So this t is a like a general t used for all time instances, and then we can take this absolute value and take the square, right? So likewise, we can find the autocovariance value. Autocovariance value will be this expression will be coming from this expression, and you can compute this, and you can see it doesn't depend on the time instances specifically, right? So there's always the time independence, right? Time independence of time independence for these statistics, right? That means that these statistics are not dependent on specific time instances, T1, T2, T3, but they are basically constant for all the time instances. So therefore, these statistics are in time independent. They are time independent statistics. Time independent statistics, right? So, so this time independency is only valid up to the this only valid up to the second order. Only static up to second order, right? Right. This is only static up to second order, right? So all the time, so this is static only up to second order. And so when we take in general about the all the random variable processes that we discuss about the strict and stationary. And when we compare these two processes, we can say that the wide and stationary is a subset of the strict and stationary. So if I can draw that, we can say that this random processes, then if there's a strict sensation random processes in this circle, the wide stationary will be only part of the strict stationary. So wide stationary will be a subset of the strict stationary processes. Right. However, like all the time that now the wide stationary processes will not always sorry yeah, strict stationary are always wide stationary. And if there's a process which is wide stationary, it will not always be strict stationary, right? So that means that if there's some kind of a wide stationary process, that will not be strict stationary process all the time, right? So which means that that we can say that there's some kind of a wide stationary process which has the statistics constant up to second order. It doesn't mean that all the nth order statistics are constant, right? So wide stationary processes uh, are a part of strict stationary, but wide stationary processes are not entirely strict stationary all the time, right? So this is not equal. WSS are not equal to SSS all the time. So this is not equal all the time, because in here only up to second order statistics are constant. Whereas in SSS, all the, statistics up to nth order are constant, right? So up to nth order, these statistics are constant under the SSS scenario. Right. So with that, I think I have discussed mostly about all the, like, strict stationary and wide stationary processes. Right. So, however, like there are like situations where these WSS and SSS are equal, and such kind of a case is the situation where we have Gaussian distribution. So these random processes that follow Gaussian distribution. So if there's a random process that follow Gaussian distribution, right? If there's a random process that follow Gaussian distribution, that process will have this feature where the wide stationary and strict stationary processes are maintained. That means that the if there's a Gaussian random process, right? That in that random process, the wide stationary, this random process will be both wide stationary and also strict stationary, which means that in the Gaussian random process, its statistics up to nth order will be static, right? It will have static statistics over the time, right? Up to nth order. So up to nth order, the statistics will be same, right? Constant statistics will be there, right? So these things I think you can actually think about another time as well. Might not be able to like go through right now itself, but for these kind of cases, maybe you can write them down and go through them one by one during your free time. So for Gaussian random processes, the statistics up to nth order will be constant over all time instances, right? Nth order statistics will be constant over all time instances, right? For all the time instances, with statistics will be equal, right? For the WSS, and so it will show WSS properties and SSS properties. So the Gaussian random process is a special random process. It's a special random process which has special distribution features and mean variance. Those statistics are very, like nice, and they are in a certain way that the statistics will be constant for up to nth order, right, over all the time instances. And the discussion that I have up to this regarding this wide sense stationary and strict sense stationary will be like that. And then I will now I will try to continue, right? However, I think I will give you a small example sum to finish by the time you come in the next class, right? So in the so I will give a small example sum to complete, right? I will give a small example sum to complete while you are there, right? So this example sum I will give in the LMS, right? So I will provide a sample sum, and I will upload that sample sum in the LMS. So you need to complete it and submit it in during a certain deadline that I give, right? So I will give some sample sum related to the strict sense stationary and wide sense stationary principles that we just discussed, right? So I will provide that sample sum in the LMS, right? So you can complete it during the your free time and before the deadline. So I think we discussed about the wide sense stationaries and strict sense stationary processes. If you have any questions, you can ask. Do you have any questions? No questions means you know a lot of all the things. So like in the next class also, I'm hoping to give a quiz just like today. So you can participate in that. So in this minutes, I will go through MATLAB simulation, which I would like to discuss about. So we discussed about something called cross correlation in today's class, right? So in this simulation also, what we are trying to do is finding that cross correlation value, and I will explain like how it is used for real world applications or real world signals, right? So I think that is something that you are interested in finding out, no? So I hope that this will be useful for you. So cross correlation functions are already available in the MATLAB software, right? So we learned about the mathematical definition of cross correlation, and that is available as a function in the MATLAB software. And that function is this X cross correlation, and it is given by this X CORR function. If you want to know about this X correlation function more, you can go to MathWorks website and learn about how it is working, right? So otherwise, you can also see its definition as a code in the MATLAB scripts, right? If you want the simpler version of understanding that, maybe you can go to the MathWorks site and type X correlation, and then you can find that. So anyway, like you can find the definition using documentation. So this documentation is same one that appears for the MathWorks. So the X correlation function can give out two outputs, right? So the cross correlation function can give two outputs. So the one output it can give is the similarity between uh, between the two uh, the two samples that we are comparing, right? So now cross correlation is something we discussed in today's class, and I told you like we are going to be discussing about two different signals in there. Right? Cross correlation is is a concept defined for two different signals, right? I don't know whether you can remember that, right? So I think I will try to go through that again. maybe share with you what I have discussed earlier, right? So in this, so I hope you can see this cross correlation. Cross correlation is the function that defines similarity between two signals X and Y. And in here MATLAB simulation, I'm going to discuss about the comparison between the X and Y, X and W signals, right? And these X signals correspond to an audio signal that I will obtain at a certain time instance. And then there's another signal which I obtain at a certain, let's say both of these are obtained at the same time instance, let's say. However, this signal has been recorded, or second signal has been transmitted at a different location from the first signal. Which is maybe 6 meters or some kind of a different location from the first one. What I mean is that there's some kind of a transmitter here, and that transmitter transmit the signal, and there's another transmitter. That transmitter also transmits the same signal, but there's a distance gap between these two signals. Let's say they are separated by 6 meters. So the distance gap between these two locations is 6 meters. There's a transmission of signals to a certain receiving point. So there's a certain receiver, and that receiver will receive signals from both these locations. And right, so this signal that the first one is transmitting, I will denote as X. The signal that the second one is transmitting, I will denote as W. Right, X, and this is W. Okay, so the receiver here will receive these two signals, right? The quality of the signals will vary. I think you can understand, because first one is coming from a near place, the second one is coming from a far away place. So when we are trying to compare these two signals, although they are transmitted at the same time instance, let's say time t1, that at the receiver end, the second signal will come with a certain delay, right? So the second signal will have a certain delay, some kind of a delay will be there. So second signal will have a certain delay, and that delay is what we are trying to estimate here. So this aspect is something essential for us, because when we are trying to combine two signals that are coming from two separate sources, two different locations, and if the same signal is occurring, we might need to combine these two signals to find out the information that is included in those signals, right? So the reason that we are trying to do is because we are trying to extract more information from the signals as much as possible, right? So it is similar to the case where we have two different calls that we are sending over the wireless communication networks, right? If we have two signals coming from two different locations, we try to combine them. But when we are combining, we need to be aware of this time delay, and this time delay will affect the output information, output that we receive from this received signal, right? So if we want to get the maximum out of all of the received signal, and if we try to decode the signal, then it's better if we can identify the delay. So in order to identify the delay, we need to find the cross correlation between these two signals. The cross correlation between these two signals. So the cross correlation we can find using the XCORR function in the MATLAB. Inside this function, we can define the two signals that we want to find the cross correlation. So the two signals in this MATLAB code are basically X and W. So we will give those two signals as the inputs to this X correlation function. And the outputs of this X correlation will be, there will be two outcomes that are possible. The first one being the similarity index, and second one being the lag index. So this similarity index will show how similar these two signals are. right? So, so in order for us to find the place where the similarity is the highest, we need to use this similarity index, right? To find the most, the most, the place where the most amount of overlap happens. The most amount of overlap happens when the similarity index is maximum, right? When the similarity index is maximum, the the most amount of overlap is happening. That means that the signals are almost same when the similarity is the maximum. So the maximum similarity that we can get will be either +1 or -1, right? So what I mean by +1 -1 is that, like, +1 comes when the two signals that we are considering are of the same polarity. So what I mean is by that is, like, the minus signs. I mean, if the signal has positive amplitudes all the time, or the polarity between the signals have same sign, then it will be same in the other signal as well. So what I mean is that in X and W signals, if the voltage values, if, let's say we are considering voltage values, the voltage values are positive in the instances we are comparing, then the same polarity is maintained. If they have, like, other polarity, so different polarities, the polarity will affect the similarity. And sometimes if it is different polarity, then it will give minus values. So the similarity will have both minus and plus values. So if the signals are different in polarity, however they are similar, however they are different in polarity. That means that if there's a voltage value that has something like this, and then there's has a shape like this, and if there's a voltage value that is very similar to the same thing, has the same amplitude values, but the values of the amplitude are minus. So if we take the similarity between these two signals, polarity will be minus, but the similarity will be +1. They are almost all the same, but amplitudes are different in direction. So because of that, the polarity value will be -1. So similarity index, therefore, will give both plus or minus values. So the maximum being +1, and the absolute value of the maximum will be +1. So if I want to find out the place where the maximum similarity happens, I need to find out uh, the index at which it is happening, and then I need to count the delay using the index that I obtained, right? So that is what we are doing in this code. So maybe if you can't understand, maybe you can look into that. But first, I think we will try to run these codes and see how these sound signals look like and sound like. Okay, so we can first, I can now, in this code, what I'm doing is I'm taking I'm sampling the sound wave, which is drum dot wave, and this drum dot wave is the first signal that is getting transmitted. This is the delayed version of that same drum signal, and it is sampled using this function, and it's stored in this variable. So you can go to these variables. You can see in the variables tab the amplitudes of the X variable. There's some value for all this time, right? The amplitude, there are different amplitudes to this X signal. And for W also, we have amplitudes, right? And then we can also use a signal analyzer app. We also have the signal analyzer tab, right? So I can also start from scratch. Signal analyzer, I can start. So you can type signal analyzer. So then you can see that in there, we can see the variables that we have in this workspace are already defined in that as well, right? So don't know whether it will start. So I already have some started version. So because of that, I think it might not work. So then I can also, I will apart, yes. Right. Then I can observe the signals from this workspace, right? I can go to this signal. So anyway, it appeared here. So I think I will go to this and I will put the signal there. And then I will remove it from here. The delayed version, I will drop in here. The delayed version I can observe in the second screen, right? The delayed version. So these are the two signals that we are trying to compare. So when we are visually seeing this, we can see there are so many kind of like same patterns occurring in these two signals. However, there's a little bit of delay in this second signal, which is not that much clear to us. I mean, the delay is too small. The delay is like millisecond delay, but right, but there's a small delay, however, right? So that delay is what we're trying to assume here, that we're trying to find here. So I will run this one also. I don't know whether you will hear that. So I will try to share the sound as well so that you can hear. So this sound you can hear. It is the first sound. Second sound is the delayed version. So there's some kind of a difference, right, between those two signals. Although they are the same signal, there's some kind of amplitude difference between those two signals. In order for us to find the similarity, I run this code and I can find out the similarity of the similarity values. So if I take the similarity value, sorry. So the similarity value I can get as like an array, considering all the different possible combinations of the two signals W and X, right? So I'm comparing W and X at all possible combinations. The similarity value I put as the I will obtain as these values. And you can observe there are minus values, plus values, all combined as the output. Depending on the polarity, the output value will change. In order for me to find the maximum point where this occurs, or maximum similarity point where the similarity is maximum, I do this operation where I take the absolute value of the similarity values and I find the maximum possible value that I can obtain, right? And then output I want, and output I obtain as the index, right? In this command, I try to find the index at which that maximum similarity occurs. So that value I can take from this command. When I run this, I can see that the maximum occurs at the index of 177,153. So this is the index at which the maximum occurs. So with this index, of course, I need some more things, right? So I need to find out exactly the time related to this index, right? So in order for me to find the time, I have to find the time index, and that I can do by this command where I put the index inside the lag value. That in here I have found the uh, lag array, right? In this is array where I have all the lags between the two the lags I have considered when I compare the correlation between the two W and X signals, right? All the lag values are inside here. So this is a certain array, so, right? I can also see that as a array here, right? So the lag values, right? So the lag values I can see, right? For all the different similarity values I got. So when the similarity is maximum, I want to find the lag value out of here, right? So the maximum similarity comes at this index that we found earlier, which was 177,153. So at that index value, I want to find the lag value. Lag value is found from this array, and the lag value should correspond to the index that I found, which is I. So inside the lag, I find the ith index, and that will correspond to the lag value. And also, if I want to find the specific time value related to the lag, I need to consider the sampling frequency. The sampling frequency I have considered for each lag, or I mean, the sampling frequency that affected the lag is this 44100. So this 44,100 is the sampling frequency I have considered. So based on that sampling frequency, the lag value can be determined. The exact lag value in terms of seconds I can determine. By dividing, I can get the seconds of delay. So I can plot, first of all, the lag value in the lag indexes and the similarity value, right? This is coming as a plot, and it is defined using this plot. So in here you can see, depending on the x value, which is the lag, the output similarity value changes like this. Similarity is very high in this position, right? So you can find at a certain lag index to 2043, this similarity is the most highest. The lag index is what is given in the x-axis. But exact time value you need to find using that equation, where the lag value can be found by dividing that lag value by the sampling frequency. So by dividing that, you can find the lag value, the total lag value in terms of seconds, right? So that you can find by evaluating this. So the output will be 0.0171. So the output is almost 17 milliseconds. So at the point where there's a delay between the where there's a delay of this 17 milliseconds, there is a point where the signals are very similar. So considering this delay, we can reverse this delay, and we can do the combining of the signals, uh, and we can get the better signal at the output. So this will avoid the signals getting cancelled out due to the out of phase conditions that they show due to this delay, right? So in order to prevent any kind of cancellation or any kind of removal of some frequency components, when we combine these two signals, we can combine them after considering the delay that is uh, existing in the second signal, for example. So considering the delay between these two signals, we can combine them appropriately in an optimal manner. And we can obtain a better signal than what we have initially. So that is what we try to do. So the first step is to find the delay, right? So that is what is possible with this simulation. So is it clear to you? And if you have any questions, you can let me know. So these are the plots that you can obtain. Right. So I think with that, I will end today's class. So if you have any questions, you can ask. And if you don't have questions, you are free to leave. So thank you so much for attending.